Welcome to the Explainer. So, if you've ever had the itch to build cool gadgets or program microcontrollers, but felt completely overwhelmed by where to even start, you are in exactly the right place. Today, we're unlocking the totally risk-free world of digital electronics prototyping.
But right off the bat, we've got to ask, can beginners really build and code real electronics without buying a single part? I know, it kind of sounds a bit too good to be true, right? Usually, learning electronics means dropping cash on starter kits, accidentally burning out parts, and dealing with a super messy desk. Well, today we're going to see exactly how a free digital sandbox makes learning without hardware completely possible.
Okay, let's dive into this. Here is our roadmap for today's level up journey. We're starting with the gateway to electronics, then moving into building your first circuit, mastering the breadboard, adding Arduino and code, and finally, we'll see how to take your projects from virtual to real. All right, let's kick things off with Section 1, the gateway to electronics. We're looking at a platform developed by Autodesk called Tinkercad. Basically, it's a completely online digital space where circuit design, 3D modeling, and coding all seamlessly meet up in one unified interface. So why start your learning journey in a virtual sandbox anyway? Well, first off, Tinkercad offers this completely free drag-and-drop interface that makes designing incredibly intuitive. It's got this comprehensive library packed with literally everything from simple LEDs to complex microcontrollers. But most importantly, it gives you a safe learning environment. There are absolutely no real-world consequences here. No burned fingers from hot soldering irons, no expensive parts to accidentally ruin. Plus, it has built-in Arduino integration, which totally removes the intimidation factor, letting you focus purely on understanding how electricity and code work together. Moving right along to Section 2, building your first circuit. Time to actually build something. Now, the fundamental rule of electronics is that every single circuit requires a power source, like a battery. Electricity needs a complete path to flow. That means we're always dealing with a positive terminal, which is typically marked with a red wire, and a negative terminal, marked with a black wire. And that brings us to the anatomy of our very first component, the LED, or light-emitting diode. To wire this up correctly, you really need to understand its physical differences. First, we have the anode. This is your positive connection, and whether you're holding a real one in your hand or using Tinkercad, it's represented by a longer, slightly bent leg. Then you've got the cathode. That's the negative connection, represented by a shorter, straight leg. You've got to match positive to positive and negative to negative, otherwise the current just won't flow and your light stays completely dark. Let's actually test that out by wiring a standard 9-volt battery straight up to our new LED. Step 1, we connect a red wire from the positive terminal of the battery right to the bent anode leg. Step 2, we take a black wire from the negative terminal over to the straight cathode leg. Just like that, we've officially completed our circuit loop. For step 3, we simply click Start Simulation in the software to crank the power on. Boom! We literally just blew out the LED. In the Tinkercad simulator, you actually get this really dramatic, funny little explosion animation right on the bulb. The software is very enthusiastically telling us that our electrical current is way too strong. A 9-volt battery pushes far too many electrons through a tiny, basic LED. Now, in the physical world, that bulb would pop, burn out, and go straight into the trash, which is super frustrating and, frankly, a waste of money. But here in our digital sandbox, we just hit the delete key, laugh it off, and figure out how to fix it. To fix our little explosion problem, we need a resistor. Measured in ohms, which is represented by the Greek letter omega, a resistor does exactly what it sounds like. It resists or slows down the flow of electrical current in a circuit. Think of electricity kind of like water flowing through a pipe. If the water pressure from the pump is way too high, the pipe bursts, right? Well, a resistor acts like a narrow valve that pinches that pipe, slowing the rushing water down so our delicate LED gets the exact safe amount of current it needs to shine brightly without popping. Now that we've got a handle on safe power flow, let's jump into Section 3, mastering the breadboard. Because while wiring parts directly to each other point to point works just fine in a computer simulation, doing that in real life requires permanent, messy soldering. If we want to rapidly prototype, test out wild ideas, and freely plug and unplug components, we absolutely need to use a breadboard. I know, to a beginner, breadboards look incredibly intimidating. They just look like these terrifying white plastic blocks covered in hundreds of tiny holes. But honestly, there's a brilliantly simple, hidden electrical logic underneath. The long rails act as distribution lines for your 5-volt power and your ground connections. Meanwhile, the inside components run vertically in tiny 5-hole columns. Underneath all that plastic, those 5 holes are actually tied together. So if you plug a wire into one hole of a column, anything plugged into the other 4 holes of that exact same column is instantly electrically connected to it. It's pretty genius.
Now, to ensure your circuits don't turn into a confusing, tangled spaghetti monster of wires, you really want to follow these breadboarding best practices. Step 1, always start by connecting your 5V power to the top positive rail. Step 2, connect your ground to the negative rail. Step 3, use tiny wires to bridge the connections from the top rails down to the bottom rails, so you have power available literally everywhere on the board. And finally, step 4, plug your LEDs, resistors, and whatever else into the vertical columns in the middle. Following these specific routing rules guarantees a clean, organized, and super reliable circuit loop.
Which brings us to section 4. Adding Arduino in code. Up until now, our circuit has just been always on or controlled by a simple manual slider switch. It's time to level up from a basic static circuit to a smart, programmable system by bringing the Arduino Uno microcontroller into our virtual workspace. So the big question, how do we make our circuits animated? How do we go from a single, boring static light glowing on a breadboard to a dynamic, cool pattern sequence where multiple LEDs flash back and forth in a specific rhythm? We do the whole shebang by using digital inputs and outputs, commanded directly by code. Tinkercad features this awesome visual drag-and-drop code block system that makes programming incredibly easy to grasp. The logic for animating an LED is broken down right here. Step 1. You tell the code to set a specific digital pin to high that pushes 5 volts of power out and turns the LED on. Step 2. You add a block to delay or wait for a set number of milliseconds. Step 3. You tell that same pin to go low, which cuts the power and turns the LED off. Step 4. You delay one more time before the loop repeats. By just snapping these simple visual blocks together across different pins, you can orchestrate some seriously complex lighting animations. Now imagine you've got 5 LEDs blinking in a row and you want to speed up the entire animation. Instead of painfully clicking and manually changing every single delay block in your workspace, you can create a variable, int animation speed. Int just stands for integer or a whole number. By dragging this one single variable block into all of your delay slots, you create a direct cause and effect. Change that single variable number at the top of your program and boom, it instantly updates the physical speed of the blinking LEDs across your entire virtual breadboard. A real game changer.
All right, let's head to section 5, our final stop from virtual to real. We've built circuits, we've safely blown up virtual LEDs to learn about resistors, we've decoded breadboards, and we've written animation code. Now it's time to talk about the absolute true power of practicing inside this digital environment.
The power of virtual prototyping is just massive. First, it allows for rapid iteration. You can literally test a dozen completely different setups in an hour without spending a single dime on physical parts. Second, the circuits you construct in the simulator perfectly mirror real-life wiring. But honestly, here's the absolute coolest part. While you're just dragging and dropping visual code blocks to animate those LEDs, Tinkercad is quietly auto-generating the actual text-based C++ code in a side window. You can literally copy that text, paste it into a physical Arduino sitting on your desk, wire up your real breadboard to match your screen, and it will work perfectly. It seamlessly builds foundational skills that carry directly over to advanced real-world engineering projects. There's a quote from our source material that just hits the nail on the head, and it sums up today's journey perfectly. Tinkercad is revolutionizing how beginners approach electronics, transforming abstract concepts into tangible, working prototypes in minutes. It truly bridges the gap. It takes these highly abstract, sometimes really intimidating theories of electrical current, resistance, and C++ programming and completely transforms them into a super accessible, visual, and highly interactive experience. So I want to leave you with this final, provocative thought. What are you going to build first? You now understand the rules of power, the vital role of a resistor, the hidden logic of a breadboard, and the pure power of Arduino code. This digital gateway is completely free, and it is just waiting for your ideas. So take this knowledge, start tinkering, and turn your imagination into reality.